Now that we've talked a bit about the universal law of gravitation, the next thing that we want to look at are planetary orbits. And to start, I'm going to give a very brief history of kind of the understanding of planetary orbits leading up to Newton, essentially. And that's going to introduce us to Kepler's three laws of planetary motion. And so the fundamental question when looking up at the stars is that there are these wandering objects that don't seem to follow the same pattern as all the other stars, and that's what the word planet means, wanderer. And so trying to understand, are there rules or laws that govern the motion of these sort of peculiar objects in the sky? And so early on, the thought put forth by Aristotle, by Ptolemy, was that the planetary orbits were circular orbits, and the planets orbited around the Earth. And so it was what's known as a geocentric model. And then considerable time later, Copernicus comes along and suggests, the orbits may be circular, but it makes more sense for all of the objects, including the Earth, to be orbiting around the Sun. And the big takeaway here is that, there was a geocentric model, there was a heliocentric model, but both required circular orbits for the planets in the solar system, and basically both types of models didn't do a great job matching the observational data that existed. And so then comes along Kepler, and again, this is very brief. I'm missing a lot of what happened over these hundreds of years. Moving on, Johannes Kepler worked as an understudy with Tycho Brahe, and Tycho Brahe had essentially the best by eye observing setup that existed at the time, and actually to this date. So Brahe observed the night sky for years and years, and this was before the telescope, and so no telescope aid, just by eye observation, and so recorded and collected just a ton of data on the stars and these wandering planets in the sky. And Kepler ended up working as an understudy to Brahe, and then when Brahe passed away, Kepler essentially dove in and began to analyze all of the data that Brahe had accumulated. And through that process, Kepler came up with three empirical laws. So these were laws based off of the data, but weren't physically motivated. There was no explanation as to why the laws were the laws. They just happened to be the rules that the planets in our solar system seem to follow. So that's where we're at. And the way that the book introduces this sort of introduces it in parallel with, this is the gravitation chapter, so Kepler's laws and the gravitation chapter, but really the universal law of gravity put forth by Newton came after Kepler's laws. So Kepler's laws were more, here's an empirical result based on the data, and then Newton came along afterwards and said, well, I can explain why those are the laws if there's just this law of gravity that governs the motion of the objects in the solar system. So keep that in mind. So three laws for planetary motion. The first law, and this is sort of the big one that allows our model for planetary motion to do better than any of these previous ones, is that the orbits aren't restricted to be circular, they're elliptical. And that is to say, with the sun at one of the focus points. So here's sort of an ellipse down here that you can take a look at. An ellipse is one of four conic sections. So a conic section is, quite ironically, literally what it sounds like, just slice a cone. And depending on how you slice the cone, you could get a circle, you could get an ellipse, you could get a parabola, and you could get a hyperbola. So depending on how you slice the cone, you get a different section. And those sections correspond, it turns out, to the orbits that you can have in planetary motion. And in general, the expression to sort of describe the conic section is this here, where alpha is a constant, E here is a constant, and the variables are r and theta. And you can see over here on my picture, r is the distance the planet is away from, in this case, the sun, which is located at one of the focus points. And theta is the angle between this major axis and that line r. So theta and r are the two variables over here. And E is known, it's a constant, and it's known as the eccentricity. And so you have these four conic sections, those correspond to four types of orbits, and the eccentricity essentially is another way to characterize or define which type of orbit you're talking about. So Kepler's first law is that the orbits are elliptical, and that is essentially this first type of orbit when the eccentricity is between 0, including 0, and up to but less than 1. So these orbits are bound. Notice how in this picture up here, right, this is a bound orbit. This planet's going to keep going around and around forever. And so the types of orbits that you can have in this first category is, in general, an ellipse, but if the eccentricity is 0, that actually turns into a circle, right? So a circle is sort of just a special type of ellipse. So these are known as bound orbits. These are the orbits for the planets in our solar system, and really any bound system. If the eccentricity is 1, that corresponds to a parabola. If the eccentricity is greater than 1, that corresponds to hyperbola. And both of these are unbounded, which I'm generically referring to flyby orbits. That means these would be orbits that the planet or the object comes in, gets closest approach, and then flings back out and essentially never returns. So flyby meaning that it's just a one-time passing occurrence and the object will not be returning. Okay, now the second law that Kepler realized was that planets sweep out equal areas in equal time, and we'll talk about what this means, but remember that Kepler was looking at observational data, and so this equal areas in equal time thing, again, not motivated by any physical law or any theory, just this is what he observed in the data. When we say equal areas in equal time, what we mean is that, so if the time interval between A, B, C, D, and E, F are all the same. So I've got this planet that's in orbit around the sun. So if the time between A and B is the same as the time between C and D, and the same as the time between E and F, if those time intervals are all the same, then this area, 1, has to be the same area as 2, has to be the same area as 3. So that's what we mean when we say equal areas in equal time. If, let's say that this is 1 month, then this, and this is 1 month, and this is 1 month, then all of these areas are the exact same size. Obviously, they're different shapes, but the area in total is the same. Now, again, not an explanation as to why this is the case. This was just purely from the data. But let's think about what the implications are. So the planet that's, when it's traveling from A to B, has to travel farther than when it's traveling from E to F. And so what that means is the planet's traveling from A to B and E to F in the same amount of time, but it's traveling much further from A to B. So that means the planet's got to be traveling faster over here than out here. And so what this second law is really getting at, although again it wasn't there wasn't any physical explanation for it, what it's really getting at, and it took Newton to come up with the universal law of gravitation to connect it, what this is really doing is telling us about the angular momentum of the system, in that when you're out here, you must be moving slower, and when you're closer to the sun, you've got to be moving faster. And so remember, angular momentum, mb times r. So when we're at between A and B, r is much smaller, so v has to be much bigger. When we're all the way out at E and F, r is much bigger, which means the speed is going to be much smaller. Right, so this Kepler's second law, again, equal areas and equal time, sounds kind of bizarre, but what it's really getting at is the conservation of angular momentum. When the planet gets closer to the host star, it moves faster, it speeds up. So as the planet is swinging around this way, it's speeding up, this looks like closest approach, so this is when it would be going fastest, and then it's slowing down until it gets out here. Now the last of Kepler's laws is that the square of the orbital period for the object in orbit, so the square of the orbital period is proportional to the cube of the semi-major axis. That's a lot of words to try to separate out in your head. It seems like it'd be much more appropriate to write that out as an equation, and that's what we're doing right here. So the square of the period is proportional, so these are just constants, proportional to the cube of the semi-major axis. And I've written out 4 pi squared over big G m, where m is the mass of the host object, so like the sun in our solar system. This is the expression for when the host mass is much, much bigger than the planet or the satellite or whatever is in orbit around the object. So an interesting thing is that if we're in the solar system, so if m is the mass of the sun, or if we're in any system where the host object is the mass of the sun, then this constant essentially turns into this. So I've just got different units. I've got years squared over AU cubed, and AU is an astronomical unit. And this is a very straightforward way to represent Kepler's third law when you're looking at objects in our solar system, because the AU, an astronomical unit, is a common distance unit when we're talking about solar system objects. So the nice thing about this form of the expression is if you have AU, if you have A and AU, you just plug that in, cube the value, notice how the units will cancel out, and then you'll be left with years squared, and then you'll take the square root and get the period. So I've actually got an example here. So let's investigate Pluto. So the semi-major axis of Pluto is about 5.87 times 10 to the 12 meters. And so if we want, we could take this value for A and we could plug it up here, plug A in meters, and then plug in G, plug in the mass of the sun, and we could do the calculation out and we could figure out the period. Now that would bring us the period in seconds, which wouldn't be a terribly useful unit, so then we want to convert to years. Instead, what I can do is I can convert this to AU and then use this version of the expression, which is much more reasonable for the result that we're going to get, because the result's going to come out in years. So remember, an AU is defined as the average orbital distance from the Earth to the Sun. That's about 1.5 times 10 to the 11 meters. So this value for Pluto, I can just scale that. So here's the value in meters, and then I'm going to divide by the 1.5 times 10 to the 11. That gives me about 39 AU. And so now that I know this orbital distance in AU units, I can just plug directly into this expression. And so that's what I'm going to do down here. I've taken the square root because it's t squared, so I've taken the square root, so I just have t on the left, square root, and then my units, and then here's a cubed. So I'm going to cube 39, and then I'm going to take the square root. And that works out to be 243 years. So Pluto is orbiting about 39 AU away from the sun. So the sun is 1 AU from, or the Earth is 1 AU from the sun. Pluto is 39 times further away. It takes the Earth 1 year to orbit the sun. It takes Pluto about 243 years to orbit the sun one time.